For the first talk today, we have Irma Pallares Torres, and she will tell us about Thom polynomials and exploratory discussion.
Thank you very much for the introduction. First of all, I would like to thank Pepe for the invitation. I am very happy to be here, and also for this opportunity to ask questions, ideas, also during the talk. So, in my talk, I will ask some questions that I asked myself some time ago, but I didn't have time to start working strongly on it. So, so I would like to formulate them here and see what about this. So also I thought on do that because I saw the participants and I see here many experts that touch all the topics that I will mention today. So for me it would be very productive to receive some feedback, comments, anything. So please, if you consider you have to interrupt me at some point, please do it. Okay. So the talk is organized in three parts. So at the beginning, I will recall Thom polynomials and hyperthom polynomials that was discussed yesterday by Jacob. So I will not spend a lot of time here, but more for focus on the notation to then formulate the questions. And also in this part, I will discuss the equivariant setting of Thom polynomials and hyperthom polynomials. I will discuss this here. And then here in the second part, I will formulate questions. So you can see here order theories of characteristic classes. So maybe many of you can now predict what kind of question can be. So this is in the line of yesterday's discussion by Richard that he discussed it's possible to construct theory of Thom polynomials for other theories, for example, Chern motivic Chern classes. So I will not focus on this, but it's in this time. And finally, I will also discuss so first applications of classical Thom polynomials, and if the questions that I formulate here are interesting, maybe one can also ask questions in this part of applications in singularities of mappings. I will focus on mappings from Cn to Cn plus 1 that are mappings that I work with at some point, so I will feel more comfortable on these mappings, so I will discuss this kind of mappings here. Well, so during the talk I will focus on mono singularity types. I will not go to the multi-singularity types, but of course the things that I can tell today can be translated to this setting, but for simplicity I will only discuss this setting. Okay? So let's consider a stable mono singularity type, and as you know, the Thom polynomial of a stable type is the unique polynomial satisfying that for any stable map. Yesterday we discussed that that part can be more general, but well, I will focus on this setting. And the fundamental class of the closure of the singularities of type eta on F can be computed as the polynomial evaluated in quotient classes. Okay, so this is the classical setting. And then if we discuss hyperthom polynomials, so first we need to talk about the characteristic classes of singular spaces, about Wagner-Persson classes. So in particular, concretely, we will discuss Segre's Wagner-Persson classes. For this, we need to consider an embedding from a algebraic variety to a smooth manifold. And the Segre's Wagner-Persson classes, as also we discussed yesterday, of the embedding is defined as first taking the Wagner-Persson class of X, and then make the product with the inverse of the total Chern class of the pullback of the tangent bundle of M. This here is seen in homology on X, but to discuss Thom polynomials, we want to see these classes on M, and also in cohomology. So now I will denote in the same way, but we can reformulate this class to have a homology class on M. Okay, so this will be the Segre class, but in an n. Okay, so I will use the same notation at some point. So Toru-Omoto proved the following theorem that given a stable monosingularity type eta, there is a unique power series such that for any stable map, the cohomology class of the associated to the Seigers-Van-Matterson class of the eta type locus of F is equal to this series evaluated in the quotient class. Okay? So this is called the Heiger-Thom polynomial. And as you know, the Heiger-Thom polynomial satisfies that the leading term is the Thom polynomial, and then we have higher order terms. But I want to also focus in this particular case that when M is compact, the Euler characteristic of the eta locus can be computed with this series, with Heiger-Thom polynomial. Okay, so this will appear later. For this reason, I also remark this here. So the point is that to prove the above theorem, Toru-Omoto used equivariant Chern classes and a version of equivariant Thom and Heiger-Thom polynomials. And in these two papers, he provides these theories, and here he provides the proof. So he introduced equivariant Chern classes for singular varieties, and then the notion of equivariant Heiger-Thom polynomials that satisfy some nice properties. So now I will discuss a bit these two parts, and you will see why I am discussing this then for the next section. So now I will not. Enter in technical details. Only now I will discuss more like not very formal way. I mean, so now we have this. So we have the Macpherson transformation, and we have this also for the equivariant setting. No? This is this Omoto proof that we have a natural transformation from the equivariant constructible functions to equivariant homology, satisfying that in the X is non-singularity variety, we have the normalization property also.
Maybe we should remark if people are using this. Toro is not here. There's a mistake in the normalization condition. So for torus, it's fine.
Okay.
If G is more general group, you can get this, but his construction does not give. You have to modify his definition to get this normalization for any.
Okay, I didn't know. Thank
you. But you fixed it, right? So there's no problem.
There's no problem.
Yeah, okay.
Just a warning, the way he constructed, and G is not just a torus, but a more general group. The thing is, if you go to Ekman world, you have two sorts of normalization. This is the one we are taking from characteristic classes, which we want, but he's following Edith Graham, the Riemann-Roch and Ekman. What you get is a normalization is the Chern class of the quotient, of the free quotient. And they differ by the tangent bound of the fibers. For torus, it doesn't matter. But for other groups, but you can get this in this form, but his proof does not prove this normalization. If the Lie algebra is commutative, you are fine. That is the property we use. But just as a remark. So you can get this, but the remark, if you cite this, used for any G, you have to be a little bit careful here.
Okay, so now to switch to the world of Thom polynomials, we need to consider a subgroup of constructible functions that are G invariant. Okay, and this set is defined in such a way, and this will be finally related with these stable types. So some invariancy is needed to then switch to Thom polynomials, and now the transformation that appeared before now can be restricted to this subgroup. And now you can consider the following composition. Take the restriction of the equivariant McPherson transformation to this subgroup, and then instead of see this in homology, we can take the inverse of the Poincare dual and go to cohomology. Okay, so we have now this transformation on the smooth variety M, and now if you consider the invariant subvariety included in the smooth variety X, and we compute the following class. So we take the constant function 1 on X, and then apply this transformation to this element. Now the leading term of all this class is the dual of the push forward of the fundamental class in the equivariant setting. Okay. And the equivariant Thom polynomial of this variety X is defined precisely by this leading term. Okay. So now we have Thom polynomials, and we can switch to higher Thom polynomials. And for this, we need to define first the equivariant Segre-McPherson class. So this is analogous to the definition, but in the equivariant setting. Okay. And now the equivariant higher Thom polynomial of X is taking the Segre-McPherson class, the equivariant version, take the push forward to this class to go to N, and then take the cohomology class associated to it. And this is the the higher Thom polynomial in the equivariant setting. So now, if M is affine and X is invariant subvariety, and we fix that it has some codimension, the terms, the classes of this higher Thom polynomial are 0 for degrees smaller than k. This really means that the leading term of the higher Thom polynomial is the Thom polynomial in the equivariant setting. Okay, so why I said all these things? Because now I will switch to other theories of characteristic classes. So, and the question was formulated yesterday, really. Would it be possible to obtain a higher Thom polynomial type theory for other theories of characteristic classes? And yesterday, Richard discussed the Motivy-Chern class version, and there is some progress on it. But my setting from my camp is from this world. So my last years I was studying Hiltebrook classes and L classes really. And for me was, instead of thinking of Motivy-Chern classes, for me was more natural from my side. Said, okay, we have Chern, Thom polynomials for Chern classes. What about Thom polynomials for these classes? For me, the next step would be try to understand what happened here. So this is the next part.
So as a comment, at the beginning we were also more interested in the Hiltebrook class, and the Motivy-Chern was just the byproduct.
Yeah.
Of course, during the development we changed our mind, and later on it turned out that the K-theoretic is a key player from which everything comes. But originally we wanted to have the Hiltebrook class.
So they are related by like a linear type state.
Yeah.
So if you know the Motivy class, you will know this.
Yeah.
Principle.
So in this part, no, another thing would be in this. Well, I know something that here is more complicated. Many of you know why, but yeah, this is for a Motivy. Then this, you take the Motivy transformation, you take the dot modification, and this is the Hiltebrook class. But on this side, Motivy class is not appearing, so I will now ask things here. Okay, let's see.
So what is the left-hand side? That's the notation for the Hilbert group.
This is the Hilbert group.
Okay.
I am here talking in the smooth case, but of course, then we will discuss everything in the singular one. Yeah, this is the Hilbert group class.
Okay.
So this is really in this classical.
I got it. I thought that's the motivation. Okay, now it's clear.
Yeah, what's the goal? You want to find a Thom polynomial, where the variables stand for the Hilbert class of.
Yes, I will formulate now in
Okay.
precise way the questions. But yeah, it's like the Thom polynomial is a polynomial on quotient classes that recovers the fundamental class of the beta locus of the stable
Yes.
type. Now the question will be: there is a polynomial or higher Thom polynomial evaluated in quotient of classes that recover something. So I go with
Okay.
on this. So I will start saying everything that is known for top classes, and then I will formulate the question. So the first thing is that top classes of vector bundles are polynomials in subclasses. This is the first thing. And now, at the beginning, you saw that I put the Euler characteristic of a eta locus. I put this because also for all of us, I think it's important also to understand invariant associated to some class. So in the case of top classes, the invariant is the Hilbert arithmetic genus. And then we have the Hilbert-Riemann-Roch theorem in this particular case. That the invariant is recovered taking the top class of the tangent bundle evaluated in the fundamental class. So this
And
is
remember Jean-Paul's talk on Atiyah-Singer index theorem. If you really stated for compact complex manifold, you really needed the Atiyah-Singer. This was not originally done by Yetsu.
yeah, you
Of course,
explained that
you shouldn't use the
one.
name Yetsu Riemann-Roch. Everything is fine and everyone calls this way. But one should remind that Yetsu could only prove it for project.
So this would be the anchor point for a normalization.
Yes.
Something to come.
Yeah.
Okay.
So this is in the smooth and vector bundle setting, and now we have dot classes for singular varieties. We have the bound Thom-McPherson transformation, that the functor in the source is the functor of coherent sheaves, and the normalization property is when X is smooth and you take the structure shape of X, the dot transformation applied to this element recovers the Poincare dual of the total dot class of the tangent bundle. And the bound Thom-McPherson dot class is this transformation applied to the structure shape. But now also we have okay, first say something about the definition because maybe this can help to the discussion about the question. I don't know. The thing is how it is defined. I will say some ideas. Yes.
The G0, we had it in our discussion. This is this K group
Yes,
of
you
G,
can.
right?
It's incoherent shapes, but I don't know, sometimes the people also denote it at K0, no?
Yes, both notions are on the market and you will never normalize this. And, so lower 0 should indicate homological notation, so that means really coherent sheaves, and upper index 0 should indicate homological notation vector bounds. And I think originally, maybe even Grothendieck, I don't know, well, maybe people attached to Grothendieck chooses G for this, but if you want to compare this with other Grothendieck groups, more natural notation is K. No, but if you just want to say K0 of an abelian category or something, this is the standard notation used usually. And then K0 is the abstract notion, but G0 was from the beginning used in for coherence. I don't know in terms of. It was a more joke. Maybe someone wanted to honor the Grothendieck, but I don't know if it was.
Okay, but it's that thing.
Yeah.
So it's fine.
Nothing more.
Okay, so I now say some words about the definition. So now we take an embedding of a possible singular variety on a smooth one. And now Van Fulton and McPherson define a homological Chern character of a coherent set depending on the embedding. Okay, I will not enter in the definition, but the thing is, when we are in the smooth case, the embedding take the identity and is recover the Poincare dual of the Chern character of the coherent set.
Of course, what is behind is that because you push forward coherent sheaf to the ambient smooth, because the ambient is smooth, you have a finite resolution by vector bonds. That is, of course, a trick, and then you apply a localized Chern character to this complex of vector bonds, which will be intrinsically there. But that is why they need this smooth, and that is why I think as a transformation they formulated in the quasi-projective context, so that you are sure you have an embedding into a smooth manifold. Yeah, you can go a little bit further, clear.
So finally, the third class of a coherent set is defined taking the pullback of the inverse total dot class of the tangent bundle of the ambient variety having with this Chern character. This is the definition. Okay, so now also we have equivariant dot classes. And after these things, I'm coming back to Thom polynomial. So yeah. Yes.
So maybe you should also mention, even if you do it in homology, of course, the algebraic geometric version was done by E.D. Graham. I think the trouble with Polinsky Sang is this is only existing as an archive paper. I think it is not. Yeah, but the ideas are correct. Maybe there's some typos in and so on. Yeah, but the thing is, I think I was discussing with Andre at some point. I think Polinsky left after this paper, mathematics was surprised. And this is I like this paper, but one should also. I think E.D. Graham, you are on the safer side. This is they do it for chow groups, but they have the map to all do. But you are in the algebraic context now, or were you sitting here? Or, yeah, maybe. Complex algebraic. And my comment with this normalization also applies here.
Editing RAM also have
they have the other normalization, but you can switch. So the difference which normalization take comes from the equivalent cohomology of a point. So that means you can just put a correction factor on the transformation, and then you get the normalization you want. It's not a big deal.
So I put here again the first slide, so the second one, that we have by Irma's theorem that there is a higher Thom polynomial that satisfies this property. And we have the particular case for the Euler characteristic. So the question now is the following. Do exist a unique power series and a class of the eta type locus in terms of Van Fulton McPherson dot class such that this kind of equality happen? This is the question. And the equivariant part that I explained here is because in Nomoto's paper he used equivariant, this setting that I explained of equivariant polynomials to prove this theorem. So I expect that if this is possible, one will need this equivariant setting for construct something like this.
The equivalent is on the market, so one can use it. So that's why. So to formulate it in terms of power series in Todd is of course just a question what you prefer. You could also write power series in Chern classes.
Yes,
well,
so,
no, be careful.
So it's true that Todd class.
Be careful.
So the thing is that
it makes a difference. Todd is with Russian coefficients in Chern classes. maybe you are right to say it's more natural to write it with integer coefficients in tot. We will see. I don't know.
So what
Yeah,
is
well,
tot
I wrote integers. I don't know if it's integers. Maybe it's few.
Ah, Or maybe Q is better.
Yeah, I
so,
think,
so if you go to Q,
but
let's
I
say
think
if
will
you
be
go to Q, it's a question. Tot should be in the end if you substitute the virtual tangent one of the mapping.
So what are those tot 1 to 2?
These are formal variables. Just variables. You can give it any name.
Polynomials and C's.
Components of the
Yeah,
No,
now,
no. You can give them abstract names. You don't term them tot. Just variables.
So just the variables, the
Yes.
Chern class is the usual one.
Variables. But in the formula, you would plug in where they ask the formula in the end. You would like to have that it really becomes tot of f. So really the tot virtual tot classes of the
Sure. I mean, I'll be confused. What does it mean? Tot 1, tot 2 are these
tot
the
1,
components
tot 2
of
are
tot
the
class?
yes, they
variables.
become the component of the tot class if you evaluate it in the end. That is so the notation is not bad to suggest what you would like to plug in.
Tot of the virtual.
Yeah, so you like I talked yesterday. I think which is the order you take? You take first the pullback of, and then you take negative zero.
Yeah, but tot of the virtual is the,
Yeah.
is what
The difference of two things. And then you
Yeah,
extend
analogous
it.
to the Chern class.
It's pullback of tot downstairs composed with tot inverse upstairs.
And then this can be replaced by Chern classes because finally they are defined as a polynomial in Chern classes. So in the end, this could be formulated in such a way or as polynomials in Chern classes, but of course are the tot classes.
So if there are motivic Chern class Thom polynomials, then this also exists. Right? This is a function.
Well, not are equal in general.
You go to
Okay,
cohomology and
okay,
specialize.
you can
In
take
the
powers of 1.
specialization, they are not equal in general.
I'm not saying equal.
In principle, you can evaluate the motivic at y equals 0, but be careful.
I will mention this later.
Okay.
She's now working with tot, and if the singularities of your space are not rational singularities,
They don't.
tot is not motivic 0. That is the problem we had in the case we were also yesterday. This is the version fitting with your structure sheaf version yesterday.
Yeah, I see.
So if you have your version for the structure sheaf language,
Right.
you can apply for a kind of tot transformation to get this tot class, I guess. But this is designed at the moment for the structure sheaf.
Yeah, I will enter on that. Okay, and if this is possible, a consequence could be the Hilbert arithmetic genus of the eta type expressed as a series in all classes. Is a particular case of that. It's like a mimic of torus theory.
But if you really want to get this arithmetic genus, you have to put this correction factor in, like in the Chern class form.
Yes, I didn't write,
Okay,
I didn't put the formula. I said that could be computed in terms of course, can appear other things. Yeah. That will depend on this class, how it is. Okay, and
Maybe just for the audience or for you also. I once made I think it was in the survey paper, Andre and Piotr have written up my lectures in Warsaw long ago. So here it's, so in Chern class story we discussed the role of McPherson and Segre class type, and one is better for push forward, one is better for pullback. And for the Thom class story, pullback is a more natural viewpoint, and that is why we take the Segre classes. If you go to the definition here and look at the definition, the Segre type classes are just these localized Chern characters. Okay? So what in the Chern class story are Segre type classes are here just localized Chern characters, which are very natural and pull back nicely. So you need pullback properties without any you don't need any transversality. And here the Segre type is really, if you look at the definition, because you take the localized Chern character, which depends on the embedding for the definition, then you make this correction factor with this tot. And if you take the Segre type version, you kill this tot again. Okay? But here it's really the localized Chern character.
That's why with this Chern variables as opposed to tot. That's why I would use Chern variables as opposed to tot variables.
Chern.
It's a matter of taste.
Yeah. But you would like to take Chern degrees, not Chern classes. Chern classes, not
Yeah,
Chern character classes. Yeah. We will see.
Okay, so the point is, since the proof of Toro-Moto for the classical theorem uses these equivariant theories, the question will be, will be possible to define a similar equivariant Hager-Thom polynomials for equivariant of classes satisfying some nice properties? I think we will need, if not, I don't know how to start to working on a possible proof or something for the moment. I think it's something quite formal, because if you have taught transformation in the equivariant setting, you make something similar to the equivariant McPherson transformation. I don't know what are the details, but seems that, well, it will not be impossible to do something like this. And
Maybe we can ask the expert. Have people studied this before? I think it's not done. Thom polynomial version of top class or something. So they off type.
I didn't find
So I was also surprised, even in Schubert calculus, it was not studied.
So after these questions, it's natural to ask also this. So the first thing is that for A classes, McPherson, but also Capel-Sanderson, as far as I know, there is not an equivariant theory yet.
There's good news. Markus Barnagel is just working on this. He lectured on my conference in Heidelberg on this. So, but it's not a serious problem. L classes only work for compact spaces, so you have to go from the algebraic group we are maybe interested in, you have to go to maximal compact subgroup and work there, but it does not change the Ekman cohomology and so on. And it will be, I guess, available next year. So.
Okay, great. But we have equivariant Hilbert classes. So I can write again the question for these classes. No? It's the same. So there is a series, of course, now depend of a parameter. Here I put Q and a class in terms of Hirzebruch classes such that this equality holds, replacing here the classical Hirzebruch classes. Okay, so now I put these slides after the discussion yesterday, because now I had this question. So the Hirzebruch class for singular varieties can be defined as this composition of transformations. This is the question that was Richard discussing yesterday, and this would really involve the one that I wrote today. This is a modification, but are the Todd classes really appearing in the construction of this Todd modification? There is a kind of relation between the K-theoretical versions of Thom polynomials and Todd Hirzebruch versions, if they exist.
And here applies, of course, the comment we made in the afternoon discussion, the comment I made. So depending which version of these characteristic classes you would like to be interested, and it should fit with a kind of nice map. So the transversality or this property of niceness you have to impose. This really changes depending which of these theories you would like to look. So I think what is classically done, this kind of stratified transversality should in the end work for all of these classes except and for Todd you don't need any condition. Todd is for free. For Todd you don't need any transversality that you started with. Because you need this kind of formulas for pullback, and for Todd this was proved by Verdier. And I think the Ekman version is in the work of Edith Graham, for example. But we have to be careful if you want to do this for these Hierro classes. You have to wait that my paper is written up with this pullback, which I mentioned in my talk in the end. This slicing down formula is okay, but it's not in public. I think that would be needed here.
And coming back to some comments before, yeah, for different values of the parameter. So for y equals -1 is the rationalized class. For y equals 0, when you see this transformation applied to the identity and then you compare with those class of the structure sheet, they are not equal in general, only in Dubois singularities, if it has Dubois singularities. And in the class is something similar happening. So they are not really the same. In some varieties, yes, but no in general.
It means just we have more options if you want to think about kind of Thom polynomial in this language. We have choices. You have to figure out which one you want, or you want to compare all of them.
But the thing is, for me, it's interesting to. So at the end, for the Hirtebro class study, so it's written in terms of motivic class, but also in the end on top classes. So independently of they are equal or not the classes, I think that maybe some kind of higher Thom polynomials in this setting and this setting also should be interesting to understand what says about which kind of connection there is.
So, do you have any idea what this class is would say about singularities of the maps besides calculating the arithmetic genus?
I will now ask things also about this and now in the next.
Maybe I just want to make this comment that I think these are all very, very interesting, but even if somebody proved the existence of these theories, I don't see any method to calculate them, except for the three special cases which seem to be related to representation theory, where this Okonkov story related to interpolation. So for those three, even though we don't know the existence, we can approximate the existence with the existence of this and this property. Then we have tools to calculate them. So that's why, yeah.
Yes, and of course it will be horribly complicated. So if you say already the Chern class story is complicated or higher Thom polynomial version, it would start to interest. It would of course it would be included in such a language if you full. The more abstract you take, the more complicated. It takes more information of the similarities, but if you can really produce it, it's very hard, I think.
I think, but so you might think that what Jakob talked about is complicated, but in fact it's not. So what happens is that if you are interested in some kind of motivic class of some degeneracy loci, and you want to do it by brute force, then you have a huge mass of 10 computer scales of formula, and then. But then what Jakob talked about is that it reduces to a very, very few information. Right? It depends on just a few theories which are linear, and then all this mass that whatever happens in the world, it all comes from the Kazarian construction of very few atoms.
But that would mean what, if I understand your comment correctly, is what we discussed yesterday, this Okonkov idea that the key player is vanishing.
That's a keeper of calculating that.
Yeah, for
calculating. The structure is independent.
No, but for calculating.
For calculating, yes.
And that would mean, for example, it will not apply to the Stott transform.
Absolutely, that's what I'm saying.
That's a problem, for example.
Yeah. So even if somebody shows me existence and structure, I won't be able to calculate it for the simplest singularity.
So this makes sense for the IC of the locus.
This would be needed if you speak of L.
Yeah.
If you want to say what is L as on a singular space.
Yeah, but that's an application of it. Even before I asked an application. So this should factor through the D module stuff, right?
But you can already start it on
Yeah, this
So it's,
factorized
possible to do it, and then it's also interesting to calculate that.
You cannot calculate more difficult. How do you calculate for this?
Oh, it would mean, but from the picture, if I understand this correctly, it would mean you would like to look at the singular locus as usual, but what you would like to measure, if the map is generically enough, or if this is analytic or something, it's pure dimensional, you can speak of the IC complex, and it should be an Euler characteristic of the IC and not of the topological Euler characteristic you look at.
You guys got the most interesting applications in the IC case.
Yeah.
Yeah,
So you have that.
It's hard to calculate. I'm not saying that.
no, but it would make sense. So if you say you start with, if I understand this Thom business, getting more and more from all your talks, you start with a kind of singularity type, which is represented in some representation space. And I would guess the only thing you need is that this is pure dimensional, which would be in most cases. Always, I don't know.
You want to represent the cycle, but
Yeah,
go ahead.
Yeah, but you want to speak of the IC complex. And the transversality you are using is really stratified transversality, because then the IC up to which normalization you are using holds back to the IC. So it would be under your map, it would be the IC of the singularity locus of the map with these singularity types. And if you say you would like to measure this by a degree, by these formulas here in writing, it would not be the topological order character, it would be the IC order. In principle, it makes sense, but the problem is always calculate. Yeah.
So now I will switch to applications. So I will discuss the setting for mappings that are from Cn to Cn plus 1. And for discuss, I will focus on an invariant there. But for this, to introduce this, I don't know if all of you are familiar with this or not. So I will start with the classical case, is the Milnor number case. And I will write up something here that will motivate why we want to study the other invariant in the case of mappings from Cn to Cn plus 1. So we are in the setting, as you know, Chern, that define a hypersurface with isolated singularity. We have the Milnor fiber. This is a wedge of spheres, and the Milnor number is the number of spheres. But the Milnor number can be computed algebraically, as you know. And there is a relation with Turina number, this inequality. And in the case of weighted homogeneous case, both invariants are the same. So now I am interested on mappings from Cn to Cn plus 1, and we have like the equivalent to the Milnor number in this setting that is called the image Milnor number. And now instead of considering isolated singularity, we need an equivalent thing in this setting is called isolated instability. Okay? And now I write this example to understand a bit how to define the image Milnor number. So consider, for example, the cast. This is the image of this map, okay, the cast. And now we perturb a bit this map in a nice way. In a nice way, I mean that this is the image of this mapping, and it has a regular part, and in this case only a double point. That are, so for n equals 1, in this context, the stable types that appear in the image of the stable perturbation that is called this kind of maps that has this situation are double points or regular points. And this increases when you go to further dimensions, okay? But so we will consider a kind of deformation that the image has these nice properties, okay? There appear stable types in the image. And the image of this stable perturbation is called the disentanglement, and it has the homotopy type of a wedge of spheres, and the number of the spheres is called the image Milnor number. And similarly as happened in the in the Milnor number, the image Milnor number can be computed through the Euler characteristic of the disentanglement. So I will be interested to applications to the image Milnor number in the Thom polynomial setting. Why? Because the thing is that in the classical case, the Milnor number can be computed algebraically, and we have this kind of Chern Milnor inequality. The thing is that it is conjectured a similar inequality in the case for the image Milnor number, and another invariant that it is equivalent in this setting to the Chern number. The thing is that this can be computed algebraically, but the image Milnor number nowadays we don't know, and this makes this inequality very difficult. And that was conjectured by David Monk in the 90s, and it is only known for n equals 1, 2, and some very few particular kind of matrix. No? So for n equals 3 is open. Yeah. So in the case of weighted homogeneous maps, this is the conjecture is that both are equal. So now we are interested to understand this image Milnor number in weighted homogeneous mappings. So the thing is that Toru-Omoto proved a theorem that allows to compute the Euler characteristic of the disentanglement for weighted homogeneous map terms using the higher Thom polynomial of some constructible function that is expressed in the stable type, so that can appear in the mapping. And then these are the Chern classes of some vector bundles that these Chern classes are determined by the weights or the degrees of the mapping. So that are very easily to compute, so the difficult part is to compute this higher Thom polynomial. So, yes.
Do you allow non-homogeneous perturbations for the disentanglement? Yeah.
So for this formula, you need to weight it homogeneous.
Yeah, the map term needs to have a weighted homogeneous representative, but then the image and the number, you need to make a disentanglement. Just this need to be.
I don't know if I understand your question. What is your question? So you can have mappings that are weighted homogeneous and you have the disentanglement.
Okay, but the disentanglement itself does not need to preserve what is routine.
You can choose it that way. You can choose it that way.
You can?
So, can you explain a bit what you mean by the right-hand side? I don't understand. So how can you divide by C and E? So where you are living, it's some localization or where you are? How should be the right-hand side a number?
Yeah, this will give a number.
Why? It's localization, that's my question. You localize at a point or something.
So how many times the Euler class you get? That's what it does. The denominator is an Euler class.
Yes.
The numerator is a multiple of the Euler class.
Yeah, but still, you evaluate this in a point or where you are.
It's an equivalent common point.
I think.
Yeah.
That is why I want to ask. If you say this is locally in the cohomology, does not make sense as well.
But I don't know what E is, so.
Yeah, sorry, I should check a bit with what
Yeah.
because that was some years ago.
What appears in the localization that you have quotient of two polynomials in one variable of the same.
Yes, is this?
Yeah. Okay. I just want to ask in which sense this formula should be read.
Yeah, both are in the same degree, and both can be expressed in terms of weights and degrees, and in some sense this cancel the
Yeah, but the problem you need, of course, at this degree is a one-dimensional space.
It's homogeneous, weighted homogeneous.
Yeah.
Okay.
I couldn't be more precise on this. But the thing is that the important thing here is that this Euler characteristic can be computed using Thom polynomials, And the good thing is that this produces a formula only in terms of weights and degrees of the mapping. So, and this is very, very nice. That is what I explain here. And the thing is that for n equals 2, David Mon obtained a formula for the Euler characteristic, and then using this previous formula, once you have the Euler characteristic, you can obtain the image Milnor number.
Can you still, since you have the slide, explain what really the image Milnor fiber is?
So the thing is, you need to you take map Chern.
Yeah, and then you stabilize.
You perturb this mapping, and in a nice way, okay, in such a way that the type of singularity, this is singular, the image, this entanglement, but has some nice singularities. Nice means stable types.
Yes. And now, what is a Milnor fiber? You still go to distinguish points, or?
So I am not talking to Milnor fibers. So we have this image, and has also.
But your XS.
XS is the image of this perturbation.
Ah, okay. That is my question. I overlooked what was the definition of.
Yeah, it's the image of a perturbation.
So this is a germ of a singular space.
And this is the one that has a multiple type of vectors of spheres or something else.
But that is not German anymore.
No, it's
This entanglement you intersect with. It's like the Milnor fiber.
Yeah, no, you intersect with an open ball.
Exactly.
Take the image and you intersect with an open ball.
So the thing for n equals 2.
It's the weight of a sphere.
Yeah, I see. Hello.
So for n equals 2, the formula for the image Milnor number in terms of the weights and degrees was given by David Mont using different methods, and was not until 20 years after that, using this formula Toru Omoto, using Richard method of between Thom polynomials, would give a formula for n equals 3. And after that, with a joint work with we compute this TPS M for dimensions 4 and 5.
And the left hand side?
So
So that way you calculate the right hand side.
yes, and then this gives the image Milnor number formula.
Oh, there's a formula for the image.
Only formula in terms of weights and degrees. So for the people that work in singularities of mapping in this context, by Mont's conjecture, we try to compute the image Milnor number in some easy way because we don't know how to understand this conjecture.
But if I understand, you want to compare it with some A codimensions, right?
Yes, yeah, I didn't talk about this now, but yeah, one should compare with other invariant that plays the role of the Turina number.
And is that determined by the weights and the degree?
Should be, no, in this conjecture is true.
There's an algebraic expression for that. There's a concrete module that you need to look at, and if you compute the dimension of a C vector space of that module, that is a codimension.
Well, my question is that cannot be two germs which have the same weight but different A codimension.
No, if the conjecture is true, no. The answer is no.
No,
Because
it's
the
inequality.
conjecture says that it will be equal to the
Oh,
Milnor
equal
number
in this case. Yes.
in the weighted.
Yes, in this case it should be.
So it's called for Hegel.
I mean, that would be perfect. If that happens, that would be very nice. we will finish the conjecture very quickly.
Right.
What are these mother's nice dimensions?
I think Guille can explain you more.
These are pairs of dimensions where you can really find a stable perturbation. It is not clear that you have a nearby stable map. When you define the disentanglement, you start with a cusp and then you have to move it to a node. And the node is stable. but in some dimensions you might not find that.
So you see, this comes from the origin, which is not from algebraic geometry, where Whitney stratification and Thom and these kind of things were coming. They come from topological stability. And they developed all this machinery of stratification to prove topological stability. That is where these dimensions pop up. I don't know what was the exact meaning there.
The topological stratification is fine. It's
That's same is
but the analytic one is not. The moduli.
So I guess my question is, matters 9 dimensions, there is a mathematical definition.
Yes.
Okay.
Martha worked his dreams with Thom had to prove this topological stability. Martha put all the details and proves this.
So in her case, when you go from a certain dimension to certain dimension plus 1, it's roughly like, if I remember right, 12 to 13. So if you go to 12 to 13, then it's nice dimensions. So stable maps are dense or smaller. But if you go from 14 to 15, then the stable maps are not dense. So you cannot even do this. And it's, as it is said, it is related to the fact in that hierarchy that I like drawing, at a certain level, the moduli stop.
So, preparing the talk, I realized if I want to say something about applications of these questions from polynomials, first I will ask this question. So, in the case of the disentanglement, is studied the Hirzebruch arithmetic genus or the Hirzebruch polynomial?
That is why I was asking how your excess is defined. Because it's not clear to me if the Hirzebruch polynomial is defined. It's not clear to me. It's not clear to me if you can speak of Kawaii of this.
Could you do it for the Milner fiber?
For Milner fiber you can do. But Milner fiber uses machinery at the start, but your thing is not something at the point.
It is.
No, it's not conic, you said. But
no, but the Milner fiber is like
huh? No. Yeah, but then you have the question is, can you write this really as a fiber of a function on something?
Yes.
Of polynomial function on an algebraic.
Yeah, the function t.
So you have a parameter t in?
Yeah.
Okay, then it's possible.
The only thing is that function will be defined on a singular.
That's fine. The machinery gives it. So I don't claim that I can calculate it, but even to give thanks to the symbol.
This is still vanishing for nearby cycles.
Yeah, you realize this as a nearby cycle.
He knows that.
Yeah, I forgot maybe that I shouldn't.
You should.
Oh, yeah, this is
no, the thing is, no. So the thing is, yes. You can realize this. You have a deformation parameter. You can realize this as germ of a Milner fiber on a switchable singular space, which is also complicated, but this is the language you need to make sense to say you can speak of Kawaii, then it comes from Hodge. So it's kind of Hodge structure on the Milner fiber, which is very complicated because the Milner fiber is not an algebraic object. So to put a Hodge structure in, you need this mixed Hodge function. But theoretically, on anything, theoretically it's possible. So then it makes sense. So you can formulate this. And
that's about the step.
No. So first you can read this, so it would make sense. And of course, it should generalize the Milner number. So if you plug in y equals -1, it should be the Milner number you are studying. So it should be a refined version of this. But then it's possible at least to define this number. Even that was not done. That makes sense.
So the thing is, I was discussing with Lily that seems that these invariants are not studying for the disentanglement because the people working in this topic is a bit not connected maybe with this invariance ability and characteristic classes. So this will be our first question. Another one is if F is weighted homogeneous and it is possible to construct these theories of thought and Hilfe-Bruchheimer Thom polynomials, these invariants could be given through a formula.
So now I get, for example, trouble. I think this what you call chi, so what should fit this thought class, so what should be a kind of
Well,
the first one.
it's invariant for each.
Yeah, but the first one should fit in the language what you start with the algebraic genus. But algebraic genus is really a language of global language of algebraic geometry of compact spaces. And I think that is not existing for germs of Milnor fiber.
I think she means y is equal to 0.
No. We have both versions.
Yeah, but in this case.
No. So the right-hand side, the chi y, you can specialize to 0. That would be the version fitting with here it's both 0.
Don't have the genus. No, sorry. You don't have the genus.
That is my comment. Chi
I
does
think
not.
she means y is equal to 0.
No. We can discuss. I think that is a question, so we can discuss this question. And I think the question is natural, and I just want to point out, in my opinion, the question for Ki you cannot even ask, because this object does not exist.
What is it for the Milnor fiber? That's what.
Yes, so you can't speak of an arithmetic genus of a Milnor fiber.
What's the problem in this case?
Generally, this is not an
You cannot speak
you
of
cannot
the-
speak
not
of
for the
this.
Milnor fiber.
That does not help that this is realized as a Milnor fiber on a singular space. This is a manifold with boundary or something. It's not an algebraic object or compact singular analytic variety. And you cannot speak of the order cover of the structure sheet on a Milnor fiber type. That does not make sense. And, so that would be a favor to say Hilsebro 0 is a more clever notion, which makes sense for me.
Sure, but you can talk about the tangent bundle, as we saw the other day. And we can just take power series or something. Just the usual.
No, you get this trouble. This is on a space boundary. So what we discussed
Yeah, it's just
yesterday,
fix
you
the
need to
boundary.
know that the boundary is trivial on the boundary.
Yeah, we fix this. I don't know if
Okay.
that's the case.
Let's say, I think that
There are many.
that's formula to make. One has to really think about if what one wants. Can you define this in some way? It's not clear. And
Are these local complete intersections? It's not fibers.
Generally, they are hypersurfaces.
Yes.
but hypersurface on singular.
So then you can assume tangent bundles.
Yes, in-
Hypersurface is on singular spaces. Or hypersurface
No.
is on singular.
They are hypersurfaces in Cn plus 1.
Okay.
You can do exactly like
So.